Okay, this will wrap up section 4.4, graphing polynomial functions. And basically what we're going to do here is just pull together all the rules and see how it'll help in sketching graphs. So I've got a polynomial function here, and what we'll do is we'll take a look at this. This is already in factored form, which is kind of nice. And we'll draw the graph or sketch an approximate graph for this function. So the way we do that is to look at this thing, use some of our rules to try and figure out what's going on here, and then sketch a graph. Well, when we look here, we're lucky. We've been given the roots, so we can go ahead and actually put those in now. We have a root at -1. So we'll cross the x-axis there or bounce off it. We have a root at -3. And we have a root at 2. So the graph is going to go through there somehow. Right off the bat, let's take a look at end behavior, see if we're coming up or down on the ends. So again, end behavior. In behavior, we want to take a look at the degree of the polynomial. Well, if I multiplied all of these out, this would be x cubed. This would be just x to the first. This would be x to the squared, if I did that. So x cubed times x squared. But if all of this gets multiplied out, remember when you multiply a base times the x, and you have exponents, the rule is you add the exponents. So 3, 4, 5, 6. So our degree here is 6. And again, we can get that by just adding these exponents. Okay. Also, if we look at a, x times x times x, that's still just a 1. That's a 1. This is a 1. A is going to be 1. Okay, and 1 is greater than 0. So by looking at these, a is n is even. So when a is even, when n is even and a is positive, then that behavior is up, up. So we know we're going up here, and we're going to be going up here. So we got that much already. That means we're going to be going down here, and we're going to have to turn around and come back up to get to this root. Question is how far down, we're not really sure, but if we pick a point in the middle and estimate how far down we go, or in other words, what would h of x be at -2, that'll give us a good idea of how far down we need to draw this thing. So let's get that. If I put -2 in here, -2 plus 1, that's -1 cubed times -2 plus 3, that's just 1. And -2 minus 2, that's -4. So that's going to equal, that's a negative. And 4 squared, -4 times -4, positive 16. So that's -16. So at h is x is -2, we're going to go down to -16. So let's go down. Let's make that -16, and we will be here. Okay, so we're going to do that. Now we're going to come back up, and then we're going to come up here, and we got to turn around and come back down to the 2. Again, how far up do we go? And In that case, when we're on the y-axis, that's a y-intercept. That's what I would like. At the y-intercept, x is 0. So all I need to do is this. Okay, when x is 0, that's 1. When x is 0, this is 3. And when x is 0, that's minus 2. So 1 cubed is 1 times 3. Minus 2 squared is a 4. 3 times 4 is 12. So we're going to go up 12. So it would be there. So we're gonna come through here somehow. Okay, and we're gonna come down here. So now the only question is, what do we do with these roots? Okay, well, let's take a look at them. And let's put them in order. Let's start with x plus 3. So my root at minus 3, that's x plus 3 to the first power. And then the next one would be minus 1 here. Whoops. X plus 1, that's cubed. And then our last root's over here. That root is 2. And that's at x minus 2 squared. Okay, so recall, we want to look at n. Is it even or odd? And then we want to find out how big it is. So for this one, well, rather than n, let's do this. This was our multiplicity rule here. So we're looking here. Here m is odd. Here m is odd. Here m is even. And then we want to look at the size of m. So as m starts getting bigger than 1, or in the case of an even, bigger than 2, we start to flatten out as we either go through or bounce off the x-axis. So if you remember, when m is odd, we're going to cross it. So here we're going to cross. Here we're going to cross. When m is even, we're going to bounce. Okay. 2 is the smallest that m can be where you bounce. So we're just going to bounce. It won't flatten out. Here, 1 is the smallest odd, so we're just going to cross. But here, that's an odd, but it's a lot bigger than 1. So here we're going to cross, but we're going to flatten out as we cross. So now we can sketch it. So at this root, we're just going to cross straight through. And we're going to come down to here. At minus 1, we're going to cross again, but we're going to kind of flatten out as we cross. So it's going to look like this. And then we're going to come up to here, turn around, and then we're going to bounce. And just bounce, not flat. And then we're going to go up. And that's the graph. All right, let's look at one more. Let me get this. Let's see, you can read it. This is an example of using all this stuff and starting with the equation here. This comes from a word problem on page 390, number 74, if you want to look at it later and take a look what I did here. But basically, this is any polynomial function right here. This models the population of insects times 100,000. So for example, if P of M equals 2, I'd have 200,000 insects. That's the idea. And then the variable m is for months. And as it shows here, if m is 1, that's January, 2 is February, all the way up to 12 for December. So we want to do it to some things here. I'm not going to do everything in the problem, but most things. What they want to do here is first find the insect population during March and October. So A, what was the pop during March, which is m equals 3, and October, which is m equals 10. I'll do the first one and then just state the second one. You can do it yourself later. All right, you can plug these numbers in here and evaluate this directly, or you can use the remainder theorem with synthetic division, which is probably a lot easier. So let's do that. So let's take March and let's put in our coefficients. Now we haven't had to do this before, but remember you have to zero fill missing powers. You also have to go all the way down to the constant term, which we don't have, so we need to add a 0 for that. So now we've got everything filled in. And again, if you remember, bring it down, multiply, add, multiply, add these, multiply, what do we get here? Add these, multiply, add these, and that's the remainder. So that means P of 3 is the same as this remainder. So that's 432 times 100,000. We've got to add 5 zeros here. Hang on a minute. 1, 2, 3, 4, 5. So that's times 100,000. So we have 43,200 insects in March. If you do the same thing for 10, I'm not going to do it, but you'll wind up with 180 here. So you'll wind up with 18,000, or 18 million insects. You can try this one yourself. Okay, that was part A. Part B, they wanted to know, when is the population dormant? Well, first, what does dormant mean? Dormant means there are no insects around. So that means P of M is 0. But what does that mean? That means, what are my zeros or my roots? In other words, I'm finding values of m that make the function 0, or I'm on the x-axis. So all we're doing here is finding zeros. We would have to eventually try to factor this, and that's going to be really difficult with this one. But we have some other tools. So first of all, we're not interested in any factors unless they equal 1 through 12, because we're only interested in zeros that, if you look at the graph down here we're going to use later, that represent a month. So right now, that's everything. Okay, 3, we already figured out 3 wasn't a 0. So we can skip 3. And also we already discovered, and you'll figure it out later, but I did the work on the side. If you put 10 in here, you're going to get a remainder of 18 or 180. So 10 is not a 0. Remember, you got to have a 0 here for this value to actually be a 0. So we can skip 10. So we're only interested in any of these as possible zeros. Now, we don't want to try each one of these in here one at a time. That's a lot of work. So let's see if we can zero it down a bit or narrow it down. Well, with this one, it's easy. We have a 1 minus 1 test. So if we look at the 1 test, remember that just means add up the coefficients here. So minus 1 plus 26 minus 217 plus 588. If that equals 0, then 1 is a root. Well, there's no way. This number's way too big. This will never zero out. So that's not equal 0. So 1 is not a root. So we eliminated that one. That's something. Okay. Let's just kind of take a quick look at some other things here. What is the degree? 4. So we know there's going to be 4 roots. It may or may not be that helpful, but let's take a look at Descartes' rule of signs. And you remember how that worked. We look at the function and we just count sign changes. So minus, plus, minus, minus, plus, minus, plus. Okay, there's our function. So we have a sign change here, a sign change here, and a sign change here. That's 3 changes. So that's 3 possible positive roots. And then to find out the negative roots, remember you evaluate this at minus m. And again, by replacing m with the negative n, the only thing that changes is whenever you have an odd degree, the sign's going to change. Because you're going to have a negative times a negative times a negative. That'll be a negative. Here, a negative squared is just a positive, no change. And here, you're going to have a negative, so it's going to change the sign. So what will happen is, wherever you have an odd degree, the sign will change. So we've got minus, and this will change to a minus. That stays a minus. And this becomes a minus. So no sign change here at all. They all stay negative. So that's 0 negative roots. Okay. And of course, we're only interested in positive roots anyways. But what does that mean here? I can have 3 positive roots. That means I'm going to have a root that repeats because I need 4 roots total to meet the degree. So I'm going to have a repeater here. We don't need to write that down, but that's something we can be aware of. Okay, so what are the possible roots? Well, we can look at the rational zeros now. But first we can see how much factoring we can do. So if I go back to the original, all of these guys share an m. And since the leading term's a negative, I'm going to factor out a negative. I'll take out a negative m. So that's going to be m3. And now the signs will all change because I'm factoring out a negative. We get 26m squared plus and minus 588. Okay, so we've done a little bit of factoring. We have a 0 actually at 0 here, but I'm interested in these zeros in here now. Okay. There's 4 terms here, but if you look and you try grouping, it's just not going to work out. So what we can do here is use the rational zeros and try and kind of come up with some possible zeros that we could try. And recall, we need P and Q. Q is the factor of the leading coefficient, that's 1. So it would normally be plus or minus 1, but since we're only interested in finding any of these that might be a 0, these are all positive, so Q is positive 1. And since eventually we're going to be looking at P over Q, that's just going to be P. We're dividing P by 1, so this doesn't matter. Take a look at these here. Factors of minus 588, we want positive factors only. So what are those factors? Well, there's a lot of them. 2 goes in here, and we're interested in 2 because that's even. So 2 is a possibility. 3, if we divide 3 into here, it's not going to go. So 3 is 3. Oh, I'm sorry. We don't even need to consider 3. So let's look at 4. 4 goes in here because there's a rule. You can either just use your calculator and see if 4 goes in here evenly, but the divisibility rule for 4 is if the last 2 digits are divisible by 4, the whole thing is. So I know 4 is good, so we'll have to try it. Okay, that doesn't end in a 0 or 5, so 5 is out. Okay. 6. As it turns out, 6 will go in. And most of these you'll just have to try. There are some divisibility rules, but it's easier to just test at this point. In other words, take your calculator, 588 divided by 6. If you get a whole number, no remainder, then it's a factor. So 6 is good, 7 is good. As it turns out, 8 doesn't work, 9 doesn't work. 10, we've already figured it's not a 0. 11 doesn't work, but 12 does work. So here's our possible factors that represent valid months. So the only thing we can do here is just start trying them. Now, since we're trying to figure out when the population is dormant, I'm going to test 12 first because my thinking is these months here, you're going to have some activity, more than likely. February, maybe, maybe not, but in December, I'm guessing there's no insects around. So that would be a good one to start with. And again, we're going to use synthetic division. We're only testing this now, not the whole thing. Just trying to find zeros here. And again, this time, if it's a 0, I should wind up with a 0 here. Then I know 12 is good. All right, so let's try that. Bring down the 1, 12. We got minus 14 times 12. That'd be minus 168. Okay, add these up. That's 49. 49 times 12, that's 588, and it works. If I add these up, I get 0. That means 12 is a root. Okay, so what do I have here? I got 12x, or m, I'm sorry. M minus 12, 12 is a root, times this right here. And then that's, instead of cubed, we'll have m squared minus 14m plus 49. Now, I could just test 2, 4, 6, and 7 doing this over and over again to see if I get any more roots, but this way is easier in this case, because this is easily factorable, so I don't have to mess around. I know what that factors into. This is just m minus 7 squared. So what are my roots? Well, there's that root we talked about, that we've got a repeater because I've got 3 positives and I need 4. So I have a root of 12, a root of 7, and this original root here, which was a 0. So 1, 2, 3, 4 roots because that repeated, and that's what we're supposed to get. So when is the population 0? Well, we're not going to count this one because there is no month 0. But the population is dormant then at these 2 months here. It'll be dormant in July and December. Okay, so we answered B. For C, they want us to graph it and just kind of roughly estimate the high and the low population and the month. So to graph it, again, we have a 0 at 0. It's kind of weird. We have a 0 at 7. And we have a 0 at 12. And if you look at these, this is, well, it's here. That's a 1, that's a 2. So we're going to, for 1, we're going to bounce. So let's go here. What we need to do here is, I don't know how far up to go, but I got a rough idea, because if I go back to March, which was here, we already figured that out. March we had 432,000. So if I go up to 432, 1, 2, 3, 4, 32, that's about here. Okay, so I'm going to get way up there, but 1, 2, 3, 1, 2, 3. I got to go a little bit further to 7, so I'm probably actually going to go a little bit higher here. So it's something like that. And then I'm going to come down, and we're gonna bounce off of here. Okay. And that's a 2, so it's just a nice bounce. And then we're going to go up again, but if you look at 10, I didn't calculate it, but it's 180. So we have 432 for March, 180 for October. So at 10, I want to go up to 180, and that's about here. And again, I'm 2 away, 3 away, so I'm going to have to come up a little bit higher here, and then come down here. And then for this one, I would go through at 12, but since this is a real world problem, we're not going to continue it on. But if you looked at the end behavior on this, which we didn't do, you would find out that it's down, down. You can check that later if you want. But in this particular problem, if we weren't talking real world stuff, like you can't have a negative population and you can't have a negative month, these curves would continue to go down, but we have to stop in quadrant 1. So C asked us to graph it. Here's the graph. And then to estimate the minimum population, well, we already know the minimum population has to be 0. And that's going to occur sometime during July. Remember, it kind of slops over a little, but we'll just say July. And then here, we get up to 432, but it's going to drift up a little bit more before it turns around. We're not sure how much, so we just estimate, let's just say 500 times 100,000 in March. So that's our estimate for when the low and the high populations occur and what they are. And that's basically it for 4.4.